approximation. We'll continue from where we left off.
This call is now being recorded.
Yes, with the independent electron pair approximation, last time we derived the working equations. So the main principle there was that you take your occupied orbitals, which is the set A, B, C, etc., and you make pairs out of them. So the set of AB pairs, that gives me my occupied pairs, and the set RS, some from the virtual orbitals that come out of Hartree-Fock, you get the unoccupied pairs of orbitals. And you will mix all determinants of the type AB to RS with the ground state. So my correlating functions are this set of doubly excited determinants where every occupied pair has turn by turn been replaced by unoccupied pairs. So last time I was inaccurate in one statement. So I said the number of variables was n into n minus 1 by 2, where n is the number of occupied orbitals or electrons. But that's not quite true. So the number of variables is this into the number of virtual orbitals into number of virtual orbitals minus 1 by 2. Because this RS is also there. So the set of variables is CAB to RS. You have n into n minus 1 by 2 AB pairs and NV into NV minus 1 by 2 RS pairs. NV is the number of virtuals. Okay, so the number of variables is basically the same as double CI. So in addition to this, you also have a C0, which is the coefficient of the ground state. So C0 plus CAB to RS, this whole set, those are your variables. But how IEPA is cheaper to compute than double CI is because IEPA consists of a set of independent equations, while double CI is one big matrix. So the dimension of the double CI matrix, so let's say this number I call M. It is M plus 1 by M plus 1. So that is the dimension of the double CI matrix, and you have to diagonalize that at one go. The number of, in IEPA on the other hand, you have, so let me call this NO, let me call this, or MO, MO, and let me call this MV. Then IPA, you have MO number of MV by MV matrices. So they are smaller diagonalizations. Okay. So that is why IEPA is cheaper than double CI. So this is a follow-up from the last class. And let me write down the... Okay, well, okay, I'll write down the working equations later. Fine. So this is the difference from double CI. Okay, now we change gear and we talk a little bit about size, consistency versus size extensivity. So note this carefully, because in Szabo-Oslund they call everything size consistency. The term size extensivity is not there in Szabo-Oslund, but there is a very clear difference. So size consistency refers to the dissociated limit. So when you have two this is the dissociated limit. So it means that if you have a system which contains two fragments A and B, which are infinitely separated spatially, then the total energy of AB should be equal to the sum of the energies of the subsystems. Okay? So this is a more or less simple concept. So because there is no interaction between the electrons and nuclei of A and the electrons and nuclei of B, the energy should be independent of each other. So if you do a computation on a super system which contains A and B but separated by an infinite distance, and you get an energy EAB, it should, and then you do two other computations, one only on A and one only on B, then the energy of the super system should be a sum of the energies of the fragments. Okay, now the other concept is size extensivity, which is more like your physics concept of extensivity. So you say mass is an extensive quantity because the more number of particles you have in an object, the mass increases. Okay? Volume is extensive. And intensive would mean, yeah? I cannot hear you, sorry.
That M0 and M IEPA.
In IEPA, it should be.
I mean, what is M0 and M?
Oh, yeah. Sorry. It should. No, it's MV by MV. You mean this one?
What are these quantities M0 and M?
I really can't hear you, so sorry.
I mean, what is this quantities M0 and MV? Those quantities are.
Oh, what are they? Oh, okay. No, M0 is equal to N into N minus 1 by 2. And MV is NV into NV minus 1 by 2. So the number of occupied pairs is M0 and number of virtual pairs is MV.
Oh.
So in IEPA, for every occupied pair, you have an MV by MV matrix which needs to be diagonalized. Okay. Yeah. So coming back to size extensivity, so this is the concept that if you have an extensive quantity like mass or volume or energy, which is the most pertinent quantity for us, it should scale with the number of particles. So in case of energy, it is of course not a linear scaling. It scales linearly only when you have non-interacting particles. But if you have interacting particles, it will not scale linearly, but it will scale with like to some power of n. So it means that the energy should be proportional to some power of n. Okay, and whatever is n, the scaling of the energy, that should remain constant for various systems. So this small n. However, this is a property that most quantum chemical theories cannot satisfy. So this is a very difficult requirement to satisfy. And it is related but independent of size consistency. So you can have a theory which is size consistent but not size extensive. Okay. You can have a theory which is size extensive but not always size consistent. And the bridge between these two, so the other concept that is related to these two, it's a bit unintuitive what it is, but it is actually the invariance with orbital rotation. So there are three different concepts, and they are interrelated. Okay. We will also talk about the invariance with orbital rotation today. We will start today, probably not finish. So what it is basically is that if you have a determinant made up of orbitals, then if you apply unitary transformation on the orbitals, which is equivalent to rotating the orbitals in space, the determinant does not change. So its energy and its properties remain the same. If that is the case for a particular theory, then you say that the theory is invariant with respect to orbital rotation. So Hartree-Fock is one such theory. So if you rotate the orbitals in the Hartree-Fock determinant, you still get the same determinant, and the energy is the same and all properties are the same. However, there are many theories which are not invariant. So if you change the, rotate the orbitals, which should do nothing to the wave function, the energy changes. So which means that there are spurious interactions in my theory. So it's not quite accurate. So whenever we develop a theory, these are the three things that we have to look into. Is our theory size extensive? Is our theory size consistent? Is our theory invariant with respect to orbital rotation? Here, one more thing is that if a theory you can show to be size extensive and invariant with respect to orbital rotation, then it is automatically size consistent. Okay, so that much is there. But the most difficult property to show is actually size extensivity. So there you are stuck, and there are many theories which are there, and people have used computations to show that, okay, this is looks like it is size extensive, but they have not been able to theoretically prove that it is size extensive. Okay. For example, CI, double CI, which you studied, is neither size extensive nor size consistent and nor invariant with respect to orbital rotation. So it fails on all three counts. However, it is, if you go to full CI, then of course all three are satisfied. Okay, because full CI is essentially an exact solution to the Schrodinger equation in the basis set limit. So the only limitation for full CI is using a small basis set or a finite basis set. Anyway, so since IEPA is a relatively simple theory, we will try to look into all these three properties for IEPA to give you an idea about what it is that we are trying to show for a given theory. So let's see. So we will again take a minimal basis hydrogen and try to show the properties of IEPA. And we will take an H2 dimer. So two H2 molecules separated by an infinite distance. I guess you have done the double CI calculation for this. So the terms should be familiar now. So here you have two occupied pairs of orbitals, and I will do a doubles excitation on both. So basically I'm covering all possible excitations. So in this case, IEPA, the IEPA wave function is equivalent to a full CI for one hydrogen. That is monomer. But if you take the super system, it is no longer equivalent to a full CI, because if you had a full CI, you would also have a quadruple excitation of all 4 electrons together. But in IEPA, you only do pair excitation, so that is missing. But the energies for each individual H2 are accurate with IEPA. And it's also the same as what you get with double CI, because then a double CI for H2 monomer is also a full CI. So it's the same energy, and I will just use that expression. You have derived it in your assignment. So that is the correlation energy for one monomer. So this is monomer, this one. And the delta quantity that we've used here, it is the difference of the orbital energies. So since this is minimal basis, we only have 2 orbitals per hydrogen, one occupied and one unoccupied. So E2 is the energy of the unoccupied orbital, E1 is the energy of the occupied orbital. And you have a set of interaction terms, the Coulomb, the 2 Coulomb integrals, and 4 of the cross Coulomb interactions and 2 exchange interactions. Okay. Now let's look at the dimer. So for the dimer, I have 4 orbitals. So I have orbital 1 and orbital 2, and I is indicates which hydrogen I'm talking about, so either 1 or 2. So I have 4 spatial orbitals in my hand. And my Hartree-Fock wave function is then a combination of the monomer wave functions. Okay. Now, for IEPA, I have to look at the set of orbitals. So my set of occupied orbitals AB. Each pair is associated with a pair correlation energy. So I have a set of pair correlation energies. So how many do we have? So we have
Ma'am,
yeah.
in delta expression, there should be like plus 4J12 and minus 2K12 now. I mean, because
Okay,
Coulomb are always additive.
I'm writing this from memory, so I may be wrong.
And exchange is negative now.
Well, this is a derived expression, so I don't. It's not. I'm not sure. It can be plus as well. But let me check sub while. Maybe I'm wrong. Half J11. So delta is, no, it says minus 4J12 plus 2K12. But you can cross check. So what did you all get? You did this right for your assignment? I think this is right. Okay, I will just put a question mark here and double check later. Okay, I don't have time to derive it now. Okay. So let me continue. So so these are the paired correlation energies. Now, how many do we have? So we have 4 choices. So there are 4 occupied orbitals, and I'm picking 2 at a time. So I have 6 of them. And if I enumerate them, they are 1, 1, 1 bar, E, 1, 2, 1, 2 bar. So I hope the notation is clear, because there are lots of subscripts and superscripts and subscripts of subscripts. Okay, so I had 1, 1, 1, 1 bar. So these are spin orbitals now. I'm writing for every pair of spin orbitals, there is a paired correlation energy. 1 is the occupied orbital, and the subscript of the 1 over here tells me which monomer I'm talking about. Okay. Similarly, you have the set of RS, and those orbitals are 2, 1, 2, 1 bar, 2, 2, 2, 2 bar. Okay. And so the number of pairs is again 4C2, which is 6. Now let me recap the working equations. So for IEPA, there are 2 working equations. You have an expression for the pair correlation energy, which is a sum over all the unique RS pairs of the expectation, not expectation value, or the matrix element of the Hamiltonian between the doubly excited determinants and the ground state. So in double CI, you would also have matrix elements between 2 doubly excited determinants. But here you only have ground state and doubly excited. You have more or less the same thing in the denominator. E0 is the Hartree-Fock energy. Okay, so this is a equation which gives you, and you also have EAB on the right. So this is an equation, not an expression. And the other equation tells you the coefficients of the correlating wave functions, and that is a sum over all the unique virtual pairs, CABTU, is equal to EAB. Okay, so these are the 2 working equations which have to be solved together to give you the EAB value. Okay. And these you have to compute with Slater's rules, the matrix elements that are involved. Okay. So what do we have to do with our example? So with our example, we basically, the quantity that we need to evaluate is this, the matrix element of the Hamiltonian between the ground state and the doubly excited states. Okay, and we have many of these doubly excited states. So we have to be careful and organized. So let's see. So let me write a general matrix element. So we need to compute psi 0, H, psi 1 So ij are the monomer number, remember. So 2k, 2 bar L. Okay. So this covers all the possibilities that we have for various ijkl. And I can expand this with Slater's rules. So this is a doubly excited one, so we don't have a sum. J 2k 2l bar minus 1i 1j bar 2 bar l 2k. Okay, and derivation is on
Hello? Yeah, when did I lose you? Let me share my screen again. Okay, till what point have you all heard? When
We need to compute that line.
Okay. So we need to compute matrix elements of the type psi0 H, doubly excited determinants. So I have now written them in terms of the explicit orbitals that we have, and I have used a general variable for my fragment number. So then I cover all possibilities. Okay. So 1i 1 bar j, 2k 2 bar l. So these are all the matrix elements that I need. Then I expand it using Slater's rules. Since this is doubly excited, then I don't have a summation. I only have the direct and exchange term. Then we do a spin integration. Okay. So in the first term, electron 1, so this is Dirac notation, electron 1 in the bra and electron 1 in the ket, they have same spin. Same as electron 2, which has again same spin. So when I do spin integration, this term will survive. In the second term, on the other hand, I have electron 1 with alpha in the bra and electron 1 with beta in the ket. So this will become 0 on spin integration. Okay. And when I do the spin integration, I'm writing my term in terms of spatial orbitals, so no bars anymore. I have 1i, 1j, 2k, 2l. So this is the spatial integral. Now let's see when they will be 0 and when they will not be 0. Okay. So if electron 1 and 2, so remember this is again electron 1, 2, 1, 2. If electron 1 and 2 are on different fragments, then this is an interaction term that will automatically be 0. because there is no interaction between 1 and 2. In that case, we exclude the possibility that the set Ik and the set Jl, they are not on the same fragment. So the only non-zero contribution is when the set Ik and the set Jl are on the same fragment. Okay. So what are the wave functions? So the contributions that are non-zero, that is when I equal to j equal to k equal to l. So are the only non-zero contributions, because if electron 1 and 2 are on different fragments, their interaction is 0. So this is a simple physical argument, and that simplifies my matrix elements to 2 of them. So I only need to evaluate H when I have 1 1, 1 bar 1, 2 1, 2 bar 1, and when I have psi 0 H, psi 1 2, 1 2 bar, 2 2, 2 2 bar. And also these values are also equal because we have 2 identical fragments. We have 2 identical fragments. So now we only need to compute one contribution. And also the pair correlation energies that we need to evaluate, we also have only 2 of them, and they are also equal. Fine. Sorry, pair correlation energies. And the pair correlation functions I can write in general. So I is either 1 or 2. That has 2i, 2r, I, psi 1i, 1i bar, 2i, 2i. Okay. So now I use the working equations A and B. So these two A and B equations. Okay, I didn't mention the fact, I didn't find out the value. And the value of each of these, why is this not scrolling? Yeah. So the value of these elements is, this is called K12. Now I guess this is sort of a wise after the event notation. So I could have called this a J12 as well, because this is only in terms of spatial orbitals, so it doesn't matter. And they are the same orbitals, so 2 and 2. But anyway, I will write it here. And so this is called K12. So using this notation and the two equations A and B, I have C11. So this is from B. You have C1111I, 2I, 2 bar I, K12 equal to E, 1i bar, and from A you have k1 2 plus 2. No, sorry, this one is from A, this one is from B, and this one is from B. So 2 delta C1i bar, 2i bar, and this is E1i bar, C1i bar, 2i bars. Okay. So these are the two equations, and when you solve the two, you will see that E1i bar is basically equal to delta minus delta square plus k12 square all to the power half, which is exactly what we got as the correlation energy of the monomer. Okay. Now then, the energy of the dimer, according to IEPA, is that it is a sum over AB of EAB, or unique pairs, so A not equal to B, and that is simply then 2 times 1E correlation. Now this is exactly what you would expect from the concept of size consistency. Okay, so this indicates that IPA is size consistent. While double CI is not. So IPA, being simpler, is more physical than double CI. It may not, so from the point of view of how much correlation energy it captures, that may well be less. But the wave function that you get from an IPA model is fulfills more physical boundary conditions, let's say, than the double CI wave function. So IPA is actually quite good in that sense. However, this size consistency comes with a caveat. So we have very slyly, I can say, considered the fact that the orbitals are actually localized on the two fragments. So that is why I could simplify the integrals and only say that two particular matrix elements contribute to my equations. But if you have degenerate orbitals in your Hartree-Fock function, then these orbitals are not unique. And you can simply rotate them to get delocalized orbitals. And then the argument that we use to simplify the number of terms that go into our equation, that may well fail. And we can end up with a non-size consistent result. And that would mean that my theory, I cannot call it size consistent. So I have to add something, a caveat with localized orbitals. Okay, while double CI is not even with localized orbitals. So the lesson to be learned here is that all three properties that we talked about, consistency, extensivity, and orbital invariance, they have to be taken together. So you cannot only talk about one thing. So you cannot say that, okay, I will just work with one particular function and then my theory is size consistent, I'm happy with that. That is not reliable because even when you do a Hartree-Fock calculation, although it is most likely that you will end up with localized orbitals, if there are degenerate orbitals, whether it is localized or delocalized can even depend on which iteration you stop at. So just changing the convergence criteria for your Hartree-Fock calculation can give you vastly different orbitals. So it is not safe to just assume that your Hartree-Fock will give you localized orbitals. Okay. Today we are almost out of time, so I'll just start on how to show invariance with respect to orbital rotations or figure out if your theory is orbital invariant or not. And we'll again use IEPA for it. So let's do invariance under orbital rotation, which basically means invariance under unitary transformation of orbitals. And this is actually very important but very difficult for theories to fulfill. So let's just go over the issues once again. So remember that in Hartree-Fock theory, the equation that we obtained in operator form, that could give us many different sets of orbitals. We then chose the canonical Hartree-Fock solution by saying that I want my orbitals to be orthogonal to each other. And when I impose the condition of orthogonality as well as normalization of the orbitals, then my canonical Hartree-Fock orbitals are unique for non-degenerate energies, orbital energies. The degenerate orbitals, you can take any linear combination of the like do a unitary transformation of the degenerate orbitals, and any of them will give you the same Hartree-Fock function and energy, because Hartree-Fock is invariant under orbital rotation. Okay. So for degenerate orbitals, unitary transformations give same Hartree-Fock wave function. Okay. But when you do correlation theories, since you are using the virtuals and occupied orbitals often in an incomplete manner, you lose this property. So again, if you did a full CI and you basically covered the full one electron space and the full many electron space. So you have covered the full functional space by taking all the orbitals, and you have covered the full many electron determinantal space, which is called the Hilbert space. So if you cover everything, then any rotation that you do in these spaces will still give you the same physical wave function and energy. But when you take bits and pieces of these spaces, whether it is the one electron space or the many electron space, in case of correlation theories, you would be curtailing the Hilbert space and you're taking some part of it. Then if you rotate the orbitals, then then what you capture in that curtailed space is different. So the amount of correlation that you include now in your wave function, that changes. So that affects the quantity of correlation energy, and that is not desirable, because in reality just rotating a wave function should not do anything. So your choice of curtailed space from the Hilbert space, that should be such that it allows your starting determinant, so that it allows your one electron wave function space to be rotated. I hope you get it. I mean, it's just so when you do a correlation theory, you generate this Hilbert space from your one electron space, right? By constructing a determinant. And you are now choosing what determinants you include in your wave function when you're doing the correlation theory. So this choice is up to you. If you can choose the set of determinants such that rotating the one electron space does not affect what physics you have in your many electron space, then that is ideal, because that is a physical requirement. But this is very difficult to do, and you see that double CI does not satisfy this. Neither does IEPA. We will also see that. Neither does IEPA. When we get to single reference coupled cluster, then you will see that we can take care of this. So that's why theories had to be improved and improved and improved, because it was so difficult to satisfy these things. Okay, no, now we are out of time, so I will not start the invariance today. We will talk about the invariance then on Monday after your quiz. Okay. So it's very interesting, and you should always keep it in mind that all three properties, only something that satisfies size extensivity, size consistency, and orbital invariance, only such a theory will be reliable for various systems. As soon as you lose the physical requirement, even one of them, you will have an inconsistent error bar. So if you do maybe a small system, you get away with it and your accuracy is fine. As soon as you go to a larger system, the accuracy remarkably changes, something you wouldn't expect. Or even among small systems, if you're doing, let's say, LIH, you are fine, and when you do something else with 4 electrons, I don't know, H4, you are not fine. Or when you are doing a system at equilibrium, you are fine. At dissociation, you're not fine. Or you're fine in both places, but you're not fine in the middle. And you cannot access a full potential energy surface experimentally. So then it is very important to realize what physical conditions are essential in a theory and where it can fail. Okay. Otherwise, you will keep doing calculations which are nonsense, and they will be wrong in some point and not wrong in others, and you will try to predict chemistry from something that is not reflecting physics. So the issues must be clear. But after saying all of this, you will see that most theories in use do not satisfy all three conditions. Okay, simply because the theories which do satisfy all three are difficult to do. So that is the current state, and there is no theory that can do all computations with equal confidence. So it's simply not there. We have the gold standard, which is full CI, but that you can only do maximum for about a 20 electron system. That's about the maximum you can do. So that's where we are, and that's why research continues. So it's good that we haven't got there yet. So anyway, today I finish here, and Monday we will complete this, and hopefully Thursday onwards we can start with coupled cluster theory, which is the closest we can get to full CI while satisfying all the physical requirements. Okay, so see you on Monday. Tomorrow is a holiday. Let me stop sharing the screen, and you can stop recording as well.